Raoult's law subtly influences our culinary endeavors, expanding on the initial points to reach a more comprehensive understanding. While we might not consciously perform calculations based on mole fractions in the kitchen, the principles underpinned by Raoult's law are at play in numerous cooking techniques, shaping the textures, flavors, and even the timing of our dishes. At its core, Raoult's law elegantly describes the relationship between the vapor pressure of a solvent and the concentration of a non-volatile solute dissolved within it. It posits that the vapor pressure of the solvent above a solution is directly proportional to the mole fraction of that solvent in the solution. This seemingly abstract law has tangible consequences in the kitchen, primarily manifesting through the colligative properties of solutions, properties that depend on the sheer number of solute particles present, regardless of their identity. One of the most direct implications of Raoult's law in the kitchen is the lowering of vapor pressure. When we introduce solutes like salt or sucrose into water, we effectively decrease the proportion of water molecules at the surface of the liquid. Consider the simple act of making a sugar syrup. By dissolving a significant amount of sugar in water, we are drastically reducing the mole fraction of water. The elevation of boiling point is a direct consequence of the lowered vapor pressure. Boiling occurs when the vapor pressure of a liquid equals the surrounding atmospheric pressure. In the culinary realm, this principle is subtly at work when we add salt to boiling water for cooking pasta or vegetables. While the increase in boiling point might be relatively small for typical salt concentrations, it does mean that the water reaches a slightly higher temperature before vigorous boiling commences. A more significant application of boiling point elevation is in candy making. The precise temperature to which a sugar syrup is heated is crucial in determining the final consistency and texture of the candy. Conversely, the depression of freezing point is another important colligative property relevant to the kitchen, particularly in the art of frozen desserts. The presence of solute particles disrupts the formation of the ordered crystal lattice structure of the solvent like water in most cases, making it more difficult for the solution to freeze. The classic example of freezing point depression in the kitchen is the traditional method of making ice cream. The ice cream base, a mixture of cream, milk, sugar, and flavorings, is placed in a container surrounded by a mixture of ice and salt. Even seemingly unrelated kitchen practices can be understood through the lens of colligative properties. For instance, the use of salt in brines not only imparts flavor but also affects the water activity and osmotic balance within food, which is related to the principles governing vapor pressure and the movement of water. In conclusion, while Raoult's law itself might not be a common topic of kitchen conversation, its implications are woven into the fabric of many cooking techniques. The lowering of vapor pressure, the elevation of boiling point, and the depression of freezing point, all direct consequences of this fundamental law, play crucial roles in processes ranging from boiling pasta to crafting delicate candies and freezing creamy desserts.